رحمة للعالمين.
How can we actually use recursion constructively? Well, let me propose that we actually introduce a third and final algorithm for sorting that hopefully does better than the two sorts thus far. We've done selection sort and bubble sort. Bubble sort we liked a little better, at least insofar as in the best case where the list is already sorted. Bubble sort's at least smarter, and it will actually terminate early, giving us a better lower bound in terms of our omega notation. But it turns out that recursion, and this is not necessarily a feature of recursion, but something we can now leverage. It turns out using recursion, we can take a fundamentally different approach to sorting a whole bunch of numbers in such a way that we can do far fewer comparisons and ideally speed up our final results. So here is the pseudocode for what we're about to see for something called merge sort. And it really is this terse. Sort the left half of numbers. Sort the right half of numbers. Merge the sorted halves. Right? This is almost sort of nonsensical because if you're asked for an algorithm to sort and you respond with, well, sort the left half, sort the right half. Like that's being sort of difficult because, well, I'm asking you for a sorting algorithm. You're just telling me to sort the left half and the right half. But implicit in that last line, merging, is a pretty powerful feature of this sort. Now, we do need another base case at the top. So let me add this. If we find ourselves with a list, an array of size 1, well, that array is obviously sorted. If there's only one element in it, there's no work to be done. So that's going to be our base case, but allowing us now in just these, 6 lines of pseudocode to actually sort some elements. But let's focus first on just a subset of this. Let's consider for a moment what it means to merge sorted halves. So Carter has wonderfully come up to volunteer here just to help us reset these numbers. Suppose that in the middle of the story we're about to tell, we have two sorted halves. I've already sorted the left half of these numbers. And indeed, 2, 4, 5, 7 is sorted from smallest to largest. And the right half appears to be already sorted. 0, 1, 3, 6, already sorted. So in my pseudocode, we're already done sorting the left half and the right half somehow. But we'll see how in a moment. Well, how do I go about merging these two halves? Well, because they're sorted already, and you want to merge them in order, I think we can flip down. We can hide all but the first numbers in each of these sublists. So here we have a half that starts with 2. And I don't really care what the other numbers are because they're clearly larger than 2. I can focus only on 2. And 0, 2. 0 also. We know that 0 is the smallest there. So let's just ignore the numbers that Carter kindly flipped down. So how do I merge these two lists into a new sorted larger list? Well, I compare the 2 on my left with the 0 on my right. Obviously, which comes first? The 0. So let me put this down here. And Carter, if you want to give us the next element. Now I have two sorted halves, but I've already plucked 1 off. So now I compare the 2 against the 1. 1 obviously comes next. So I'm going to take out the 1 and put it in place here. Now I'm going to compare the two halves again. 2 and 3, which do I merge first? Obviously, the 2 comes next. And now notice, each time I do this, my hands are theoretically making forward progress. I'm not doubling back like I kept doing with selection sort or bubble sort, back and forth, back and forth. My fingers are constantly advancing forward. And that's going to be a key detail. So I compare 4 and 3. 3, obviously. I compare 4 and 6. 4, obviously. I compare 5 and 6, 5 obviously. And then I compare 7 and 6, 6 of course. And then lastly, we have just one element left. And even though I'm kind of moving awkwardly as a human, my hands technically were only moving to the right. I was never looping back, doing something again and again. And that's perhaps the intuition and just enough room for the 7. So that then is how you would merge two sorted halves. We started with left half sorted, right half sorted. And merging is just like what you would do as a human. And Carter just flipped the numbers down. So our focus was only on the smallest elements in each. Any questions before we forge ahead with what it means then to be merged in this way? This will be sort of the hardest algorithm, if you will, to kind of follow. Thank you, Carter. But we'll consider now how we might do this. And then we'll do a visualization as well. So actually, Carter, can you let's put this back in order here as quickly as we can. That's why. All right, let me turn all of these off. So we're going to reset them to this order. So 2 will be over here. Oh, nope, not this order. There we go. 7, 2, 5. So we're going to put them into this order here. 7, thank you. All right. 7, 2, 5 is going to come here. All right. 4. Oops, sorry. I kind of need room for 4. Thank you. All right. Thank you. And 5. All right. Thank you. Thank you, Carter. All right. So now I think I'm good on my own. So now here is an original list. We deliberately put it at the top because there's one detail of merge sort that's key. Merge sort is technically going to use a little more space. And so whereas previously we just kept moving our humans around and swapping people and making sure they stayed ultimately in the original positions, with merge sort pretends that here's our original array of memory. I'm going to need at least one other array of memory. And I'm going to cheat, and I'm going to use even more memory. But technically, I could actually go back and forth between one array and a secondary array. But it is going to take me more space. So how do I go about implementing merge sort on this code? Well, let's consider this. Here's an array of size 8. If only one number quit, obviously not applicable. So let's focus on the juicy part there. Sort the left half of the numbers. All right, how do I sort the left half of the numbers? I'm going to just nudge them over just to be clear which is the left half. Here is now a sub list of size 4. How do I sort the left half? Well, do I have an algorithm for sorting? Yeah, what do I do? Here's a list of size 4. How do I sort it? What's step 1? Sort the left half. So I now sort of conceptually in my mind take this sublist of size 4 and I sort it by first sorting the left half, focusing now on the 7 and 2. All right, here's a list of size 2. How do I sort a list of size 2? Sorry? I think we just keep following our instructions. Sort the left half. All right, here is a list of size 1. How do I sort a list of size 1? I'm done. Like, it's done. So I leave this alone. What was the next step in the story? I've just sorted the left half of the left half of the left half. What comes next? I sort the right half of the left half of the left half. And I'm done, because it's just a list of size 1. What comes after this? Merge. So this is where it gets a little trippy, because you have to remember where we're pausing the story to do things recursively again and again. But if I've just sorted the left half and I've just sorted the right half, now I merge them together. This is a super short list, so we don't need Carter's help here as before. But I think the first number I take here is the 2. And then the second number I take, because it's the only option, is the 7. But what's nice now is that notice the left half of the left half is indeed sorted, because I trivially sorted the left half of it and the right half of it, but then merging is really where the magic happens. All right, again, if you rewind now in your mind, if I've just sorted the left half of the left half, what happens next? Sort the right half of the left half. So again, you kind of rewind in time. So how do I do this? I've got a list of size 2. I sort the left half, just the 5, done. Sort the right half, 4, done. Now the interesting part, I merge the left half and the right half of the right half of the left half. So what do? 4 comes down here. 5 comes down here. And now, notice what I have. Left half is sorted. Right half is sorted. If you rewind in time, where is my next step? 3? Merge the 2 halves. And so this is what Carter helped me do before. Let's focus only on the smallest elements just so there's less distraction. I compare the 2 and the 4. 2 comes first, so let's obviously put that here. Now I compare the new beginning of this list and the old beginning of this list. 4 obviously comes next. And now I compare the 7 against the 5. 5 obviously comes next. And now lastly, I'm left with one number. So now I'm down to the 7. So even if you've kind of lost track of some of the nuances here, if you just kind of take a step back, we have the original right half here still untouched. But the left half of the original input is now indeed sorted. All by way of doing sorting left half, right half, but with those merges in between. All right, so if we've just sorted the left half, we rewind all the way to the beginning. What do I now do? All right, so sort the right half. So sort the right half. How do I sort a list of size 4? Well, I first sort the left half, the 1 and the 6. How do I sort a list of size 2? You sort the left half. Just the number 1. Obviously, there's no work to be done. Done, sorting the left half. 6, done, sorting the right half. Now, what do? I merge the left half here with the right half here. And that one's pretty straightforward. Now what do? I've just merged. So now I've just sorted the left half of the right half. So now I sort the right half of the right half. So I consider the 0, done. I consider the 3, done. I now merge these two together. 0, of course, comes first. Then comes the 3. And now I'm at the point of the story where I've sorted the left half of the right half and the right half of the right half. So step 3 is merge. And I'll do it again like we did with Carter. All right, 1 and 0. Obviously, the 0 comes first. Now compare the 1 and the 3. Obviously, the 1 comes first. Compare the 6 and the 3. Obviously, the 3. And then lastly, the 6th. So now where are we? We've taken the left half of the whole thing and sorted it. We then took the right half of the whole thing and sorted it. So now we're at lastly, step 3 for the last time. What do? Merge. And so just to be consistent, let me push these down. And let's compare left hand to right hand, noticing that they only make forward progress, none of this back and forth comparisons. 2 and 0, of course, the 0. So we'll put that in place. 2 and 1, of course, the 1. So we put that in place. 2 and 3, we merge in, of course, the 2 in this case. 4 and 3, we now merge in the 3 in this case. 4 and 6, we now merge, of course, the 4 in place. And now we compare 5 and 6. We keep the 5. Bug. OK, well, pretend that the 5 is on. Oh, this is why. All right, so now we compare the 7 and the 6. 6th is gone. And lastly, 7 is the last one in place. And even though I grant that of all the algorithms, this is probably the hardest one to stay on top of, especially when I'm doing it as a voiceover, realize that what we've just done is only those 3 steps recursively. We started with a list of size 8. We sorted the left half. We sorted the right half. And then we merged the 2 together. But if you go down each of those rabbit holes, so to speak, sorting the left half involves sorting the left half of the left half and the right half of the left half, and so forth. But this germ of an idea of really dividing and conquering the problem, not such that you're having the problem and only dealing with one half. Clearly, we're sorting one half and the other half and merging them together ultimately. It does still lead us to the same solution. And if we visualize the remnants of this now, if I depict this as follows, where on the screen here, you see where the numbers originally started in the top row from left to right. Essentially, even though this is in a different order, I divided that list of size 8 ultimately into 8 lists of size 1. And that's where the base case kicked in and just said, OK, we're done sorting that. And after that, logically, I then merged 2 lists of size 1 into many lists of size 2. And those lists of size 2 into lists of size 4. And finally, the lists of size 4 into one big list sorted of size 8. And so I put forth this picture with the little line indicators here because how many times did I divide in half? Or really double, double, double. So exponent is the opposite. Oh, spoiler. How many times did I divide? So 3 concretely. But if there's 8 elements total and there's n more generally, it really is a matter of dividing and conquering log n times. You start this, and you can divide 1, 2, 3 times, log n times. Or conversely, you can start here and exponentially double, double, double 3 times, which is log n. But on every row, every shelf, literally, I made a fuss about pointing my hands only from the left to the right, constantly advancing them, such that every time I did those merges, I touched every element once and only once. There was none of this back and forth on stage. So if I'm doing something log n times, or if I'm doing rather n things log n times, what would be our big O formula perhaps? N things log n times? Yeah, so n log n. The order of n log n is indeed how we would describe the running time of merge sort. And so of all of the sorts thus far, we've seen that merge sort here actually is n log n, which is strictly better than n squared, which is where both selection sort and bubble sort landed. But it's also slower than linear search, for instance. But you would rather expect that. If you have to do a lot of work up front sorting some elements versus just searching them, you're going to have to put in more effort. And so the question of whether or not you should just search something blindly with linear search and not bother sorting it really boils down to, can you afford to spend this amount of time? And if you're the Googles of the world, odds are you don't want to be searching their database linearly every time. Why? Because you can sort it once and then benefit millions, billions of people subsequently using something like binary search, or frankly, in practice, something even fancier and faster than binary search. But there's always going to be this trade-off. You can achieve binary search only if the elements are sorted. How much does it cost you to sort them? Well, maybe n squared if you use some of the earlier algorithms. But it turns out n log n is pretty fast as well. So at the end of the day, these running times involve trade-offs. And indeed, in merge sort 2, I should note that the lower bound on merge sort is also going to be omega of n log n. As such, we can describe it in terms of our theta notation, saying that merge sort is indeed in theta of n log n. So generally speaking, probably better to use something like merge sort or some other algorithm that's in n log n. In practice, most programmers are not implementing these sorting algorithms themselves. Odds are they're using a library off the shelf that themselves have made the decision as to which of these algorithms to do. But generally speaking, and we're seeing now this for the first time, if you want to improve time, like use less time, write faster code, you've got to pay a price. And that might be your human time, just takes you more time to code up something more sophisticated, more difficult to implement, or you need to spend something like space. And as these shelves suggest, that too is one of the key details of merge sort. You can't just have the elements swapping in place. You need at least an auxiliary array so that when you do the merging, you have a place to put them. And this is excessive, this amount of memory. I could have just gone back and forth between top shelf and bottom shelf, but it's a little more interesting to go top down. But you do need more space. Back in the day, decades ago, space was really expensive. And so you know what? It might have been better to not use merge sort, use bubble sort or selection sort even, or some other algorithm altogether. Nowadays, space is relatively cheap, and so these are more acceptable trade-offs. But it totally depends on the application. The very last thing we thought we'd do is show you an actual comparison of some of these sorting algorithms. It's about 60 seconds long, and it will compare for you selection sort, bubble sort, and merge sort in parallel, simultaneously, with some fun sorting music, showing you ultimately what it really means to be an O of n squared, or better yet, big O of n log n. If we could dim the lights for drama's sake. Selection on the top, bubble on the bottom, merge in the middle. All right, that's it for CS50. We'll see you next time.